let's see. Yeah, what we're going to do is talk about a little bit more about centripetal acceleration, and then we're going to apply centripetal acceleration concepts, circular motion, to a very famous problem, the circular path of the moon about the Earth. And that's what Sir Isaac Newton did when he developed the theory of universal gravitation. When we're done with that, we'll be completed of all the topics for exam 1. And I'll tell you a little bit about how to prepare yourself mentally for exam 1. There'll be some homework this weekend. Tonight or this afternoon right after class, don't forget you have the special SI review over in Nicholson. And then Monday, there's a regular SI session, so hopefully you can make one or two or both of those sessions and get a little bit going for the exam. Now, I believe there's a question from the front row, from the second row. Yeah. What was your question? Oh, the with the two arrows, and one of them was 6 degrees apart, and then 4, and 2, and then 1. Students, I should have had some slides for that homework to follow up with you. The reason that those problems were in there was to show you that the base of the isosceles triangle, the smaller the peak angle gets, the closer the base angle gets to 90. Now that's important because the limit, sharper and sharper triangles is 90 degrees. And that means that the base of the isosceles the base of the isosceles velocity triangle, that's delta V, that points directly toward the center of the circle. And that's what makes it centripetal. And so that's why, so what I'll do is for the homework over the weekend, I guess it'll be homework 4. I'll put a couple 3 wrap-up problems for that, just to bring it all the way home and stuff. So, and I'm sorry I don't have a slide for that, but verbally that's what those problems are about. Any other questions about the HW? Before we continue. Okay, I have a question for you. Raise your hand if you're either elementary or secondary ed major or early childhood. Raise your hand high. Okay, that's great. Now, the reason I bring that up, you may think that this class is, you're forced to take it, you got to do GEP classes and stuff. One of my TAs, my undergraduate TAs, most of my undergraduate TAs are elementary or secondary ed majors, and I'm going to be looking for some new ones. So I might be calling on some of you guys that are ed majors. And just so you know, one of my TAs she just had a baby, but so she's not working now. But before she had her baby, she was in charge of science development for all the secondary teachers in Orange County. And so, and this was one of the science classes that she took. Another one, she lives up in Memphis, and she took this class and I think one other science class, and she became the chairman of the science department for her entire elementary school. All right, within a year or two of getting hired there. So this class can be quite valuable for you as an ed major, or anybody else for that matter. because the more that, as the years go by, our culture becomes more and more scientific. And so um, let's talk about centripetal acceleration. Take a look at this diagram here. Um, yeah, take a look at this diagram. It's a photo. You see this person over here on the left side? That's a normal human being. This is a centrifuge. And what they do, they use this to train NASA astronauts um, and give them artificially a certain number of G's of acceleration to see how they can withstand it. Because when you're under G forces, you can black out. You can lose consciousness. If you're in the cockpit of an airplane, you can crash. So they want to be able to train these guys to withstand G forces. And if you're a person that can't take a lot of G forces, you get washed out. It's just the way it is. But anyway, so what this thing does is it spins. Now, what I did was I estimated the size of it based on this photograph. So here's my estimation. First of all, we have this radius here, and we also have the height of this lady over here to the right or to the left. Okay, so I just decided, all right, let's make her 5 foot 5 inches. That's 65 inches. And the number of pixels in that yellow segment was 91 pixels. And the dotted line segment, the radius, is 459 pixels on my computer. So I said, all right, just do the proportions and convert that into inches. And it appears to be a radius of about 27.3 feet. Or 8.35 meters. So go ahead and write down radius equals 8.35 meters. Because we're going to calculate the rotational speed of a centrifuge like this that's producing some G's for astronauts in training. All right, so one of the things that we need is the spin radius. How big of a circle does it follow? All right, so here we go. So here's the close-up picture of this lady. And we're going to do 2 acceleration examples. First one, the NASA centrifuge for placing astronauts into a bunch of G's. And here's what we're going to do. We're going to set this up, and we're going to say to ourselves, okay, I want my trainee astronaut to go through 3.3 G's. Now, the reason that I chose 3.3 G's, that is about the maximum that you get in the space shuttle when the space shuttle is in launch phase. Right? So you're driven into your seat. They're in seats that are inclined, they're flat, and so their eyeballs are looking upward, and they're taking off, and they experience about 3.3 G's of upward acceleration. So their seats accelerate into them at 3.3 G's, and so it feels like they're sinking into the seat, 3.3 times their normal weight. All right, so what we're going to do is this example, 3.3 G's. So the basic formula up here, A subscript C, centripetal acceleration, V squared over R. We're going to put 3.3 meters per second. Uh-oh. You know what? I didn't put 3.3 G's. That's not a G. That's 3.3 meters per second squared. All right. Let me pause that. Okay, so this looks better now. Okay, so we're going to set it to something fairly easy for them, 3.3 meters per second squared. So that goes in on the left side in the equation up on the top in that first equation block. Now on the right side, we have V squared over R. Now we don't know what V is. I have to set that. So I'm in the control booth, and I said, all right, I'm gonna rev it up to the right speed so that those guys get 3.3 meters per second squared of extra centripetal acceleration. All right, so So my radius, 8.35 meters. And hey, you guys, that corresponds to a circumference. Better write this down. Circumference is about 52.5 meters. Now, so if your radius is 8.35, which we estimated it at from that photo, then your circumference. Now, the reason we're going to do that is because I want to figure out how many revolutions per minute. So one revolution is 52.5 meters. And this thing's going to be turning several times per minute. So, and we're going to figure that out as soon as we get V. All right, so if you look at that top equation block, you can see that V squared is the only thing we don't have a number for. So we can calculate it. We'll just do a little bit of algebra. Here we go. Cross multiply 8.35 meters to the other side, and then just rewrite it. V squared equals 8.35 meters times acceleration 3.3 meters per second squared. All right, so that's nice. Okay, and now you just got to calculate it. And anybody verify me on that? Get your calculator and get your clicker because you're about to do a clicker question. Okay, you got it? Raise your hand if you verify me. Get your calculator. That's not raising your hand. That's going like this. This is raising your hand. Okay, good. All right, good. I see you guys. All right, now get your calculators out because I'm about to ask you a clicker question. And it's not going to be on the screen. I'm just going to ask you verbally. All right? And it's going to be a numeric question. So hit the refresh key on your calculator, or excuse me, the refresh key on your clicker. And then riddle me this. V squared is 27.55. What is V equal to? To the nearest point something something, to the nearest hundredth of a meter per second. What's V equal to? Go ahead and calculate that with your calculator, and then type in something, point something, something, and hit the send key. Yeah, so hit the send key and you'll get a check mark. Let me start. Okay. All right, it should start in just a second. Go ahead and hit your refresh key again. Let's see if you get the go night. Let me try it too. All right, go ahead. Something, point something, something. Nearest hundredth of a meter per second. So the nearest 0.01 meter per second of speed. All right. So V squared is 27.55. So it's going to be 5 point something. Exactly what is it? Go ahead and type in your answers. And let me see what you guys are voting for. Okay, you're doing pretty good. Uh-oh, I see some round off problems, but now when you guys are here on Tuesday doing your exams, the last 2-3 problems on the test will actually be clicker items. So you might have 47 dots and then two clicker questions, a 1-pointer and a 2-pointer for the last 3 points of the test. And you'll be typing them in and hit the send key and stuff like that. Okay, 30 seconds. And the nice thing about having a calculation with a clicker question is that I can look at your answers in a spreadsheet. The iClicker software generates a big spreadsheet of all your numbers that you type in, and I can just look at that and grade it. And you know, if I see, matter of fact, I'll show you what it looks like. Okay, 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Now let me look at these results. All right. Let me bring this over for guys. Now look at these results. Okay, now this one up here, 5.25, is correct. And this one, a little bit low. So that one might get, instead of 3 points for the full answer, I might give this one 2 because they rounded off a little bit. It's not quite the right round off. Here's 5.3, another round off problem. 13.77. I wonder how you get that. Here's 5, too much round off, et cetera, et cetera. So, so now this is a little, a bar chart. But when we do the exam, you won't be seeing that. I'll be seeing it, and I'll be able to analyze it in a spreadsheet. It's even more convenient than doing that. And I'll be able to give you partial credit. So if you don't round, if it's supposed to be 5.25 and you round it off to 5.24, I'll say, okay, well, they're kind of in the right ballpark. But they goofed up a little bit on the rounding. Give them 2 out of 3 instead of 3 out of 3. It just seems good. And usually students like that.
What does the A
subscript C stands for centripetal acceleration. All right. And that's the formula for centripetal acceleration. All right. So here's your answer, 5.25. Now let's do some more deluxe calculations with that. The circumference is 52.5. The speed, 5.25. Do you guys remember about how, the conversion from 1 meter per second to so many miles per hour? Anybody remember about? Kelly? No? I see you're here. Yeah. What do you think, Daniel? It's 1 meter per second is about 2.24. So this one is about 12 miles per hour, a little bit less than 12. All right. And so that's a normal speed, So, for if you're at NASA and you're doing a little warm up centrifugal acceleration, 12 miles per hour, that's not too bodacious, but they get that thing, when they want to give them some G's, they really get that thing swinging. And, and then you get off and you're, stumbling around like, like you're all dizzy and stuff like that. Now, as I mentioned, the circumference, 2 pi r, is 52.5 meters. And it just happens to work out nicely that one revolution takes about 10 seconds at this speed. All right. So how many RPM is that going to be? Revolutions per minute. 10 seconds for one full revolution. How many RPMs is that going to be? See, because I'm going to ask you, what if I ask you a question like this on the test? How many RPMs? Raise your hand if you can make a deduction or you want to make a wild, crazy guess. Daniel. Correctamente. It's about 6 RPM. All right, so that's not too bodacious. 6 revolutions per minute. And if they want to build them up to higher levels of G, yeah, just go to town. Rev up the motor, get it spinning faster and faster, and it'll be good. Now, let's do another example. Example number 2. It's going to be a little bit simpler than just car turning circles in the parking lot at Publix. All right, so let's try this one. Next page. And let's just say that the speed of the car, 5 meters per second, which is, that's good. That's about 11 miles per hour. All right. And let's say that the turning radius is 20 meters. All right, so you can do that. You're in the parking lot, but most of the time the parking lot's got a bunch of cars. But late at night, you might be able to turn radii, about 20 meters. All right, so let's go to the calculation over here. A subscript c, centripetal acceleration, Sean, is v squared over r. So this one, you just plug in the numbers that you know. I gave you the speed, v, 5 meters per second, quantity squared, and then the radii, 20 meters. All right. And this is, this is pretty doable. You could go around a 20-meter radius circle at 11 miles per hour without a problem. So the numerator is 25 meters squared per second squared. Hey, you guys, cancel meters in the denominator and then 1 unit of meters in the numerator. So you're left with 1 unit of meters uncanceled in the numerator and then per second squared in the numerator. All right, so meters per second squared is an acceleration. So we're looking good here. And when you're doing your calculations next Tuesday, and there'll be room on the exam, you'll be able to write on your exam and do your scratch work in the margins, and there's open areas in the last page or two, and you'll be able to do this and check your cancellation and stuff. So the acceleration here, 1.25 meters per second squared. So that's that's not too bodacious. All right, and that's like, it's not even a full G. All right, now I'm going to pause the YouTube here for just a second. I got to make another correction. Get my cursor. Okay, so as I mentioned, that's an easy. So your grandma could take an acceleration like that without too much problem. You're gonna feel it. You're gonna have to lean into the circle, into the turn, and everything. But it's not gonna cause you to black out or anything. By the way, I was reading about it this morning. Pilots for NASA and the Air Force and the Navy and stuff, they can take up to about 10 G's of acceleration before they start, but they have to train to do that. When they just come in from boot camp, they're not going to be able to do that. And they wear G suits, the special G suits that prevent the blood from pooling down in their extremities and stuff, so keep more of their blood up in their coconut, and they don't black out. But apparently you can black out, and then that's a disaster. Okay, you lose control of the plane. All right, now that's centripetal acceleration, and we're going to use it now to talk about universal gravitation and Sir Isaac Newton's great development in the 1600s. And what we're going to do is use the concepts of uniform circular motion and centripetal acceleration to kind of leverage the little that Sir Isaac Newton knew about the moon and its orbit around the Earth to figure out the forces acting, the F equals ma, on the moon. And what he did was he found that he knew the period, the orbital period, 28 point something days for the moon. And they had a fairly good estimate of the radius. Now, those two numbers, the radius of the moon's orbit and the distance and the orbital period, he was able to figure out the orbital speed and therefore the orbital acceleration. And what he found was that the distance, well, let's keep going through here. He found that the distance from the center of the Earth to the surface of the Earth was 1/60th of the distance from the center of the Earth to the center of the moon. The accelerations were in the ratio 9.8, and then the acceleration of the moon was 1/3600th of that. And 1 over 3600 is 60 squared. And Sir Isaac Newton said, you know what? I do not think that that is a coincidence. And that's how he decided to develop his theory of gravity. And he said, okay, it depends on two and only two physical factors, the mass of the object and their distance apart. And the more mass you have, the more force. So you are getting a bunch of newtons of downward weight force from the Earth, and theoretically you're getting newtons of weight force toward the moon. But you don't really respond to that very much because the moon is so far away and the center of the Earth is so much closer. So most of the force, gravitational force that we feel as individual humanoids here on the surface of the Earth is from the Earth. But can you think of anything that you've ever seen in everyday life that does respond to the gravitational attraction of the moon? Yeah, tides. Tides in the ocean. The tides in the high tide is it's not perfectly underneath the moon, but wherever the moon is, the high tide is. It takes a little bit of time for the water to move over to where it wants to be, right underneath the moon. So there's a little bit of a lag, but yeah, high tide is right underneath, pretty close to right underneath the moon. And then the other high tide is on the other side of the Earth, where the Earth is getting tugged. The entire Earth is getting tugged toward the moon, a little bit bigger acceleration than the water on the far side. So the water tends to pile up on the far side of the Earth. By the way, you can make a note of this. We actually get tidal effects much smaller but measurable from the sun. The sun, when the sun and the moon, when we have an eclipse, a lunar or a solar eclipse, we tend to have really big high tides because the sun and the moon, if we have a solar eclipse, that means that, the Earth is here, the moon is right here, and, the sun is way over there, and the moon is blocking out the sun. So what that means is that they're all in line. So the gravitational force of the moon on the oceans of the Earth and the gravitational force of the sun on the ocean of the Earth are right in line. So they coordinate completely, and you get nice high tides and really deep low tides, okay, whenever there's a lunar or a solar eclipse. Okay. The other thing he said was the more distance you have, the weaker the force. So this is the formula that he came up with. All right. The force of gravity, according to Sir Isaac Newton, you take the mass in kilograms of your two objects. So the Earth and the moon, a kilogram bottle of water and the moon, whatever M1 and M2, the two objects that are gravitationally interacting. And then you divide by the square of the distance, r squared. So you go center of the sun, center of the Earth to the center of the moon. Center of mass to center of mass. That's your r. Then you square it, and you put it downstairs in the denominator. Now, a newton is a kilogram meters per second squared. It's a kilogram times an acceleration. M1, M2 is kilograms squared in the numerator, and r squared is meter squared in the denominator. So there has to be a conversion factor so that you multiply those two physical factors and you have the right physical factors, but you don't have the right units. And that's what capital G does. Capital G is known as Newton's constant, or the gravitational constant, and it converts it converts kilograms squared per meter squared into newtons, kilogram meter per second squared. All right, and it's called Newton's constant, the gravitational constant, at capital G, and it's kind of an interesting thing, you know. And when I say conversion constant, it's what I mean by that is, you know, like if you, the way I like to explain it is, if you know, if you remember from like middle school, converting from Fahrenheit to Celsius, you know, which I hate, you know, I just prefer to work either in Fahrenheit for everyday things or the Celsius scale for scientific stuff. But when you're converting from Celsius, you know, you have to subtract 32 and you have to add 32. That's because the freezing point of water is 32 Fahrenheit and 0 Celsius. And then you have to multiply by a factor of 9/5 or 5/9. Remember that? And that's because there's 180 degrees between boiling and melting for water in the Fahrenheit scale and only 100 in the Celsius scale. So 180 divided by 100 is 9 divided by 5. And so that's why that factor shows up. And that's converting Celsius degrees into Fahrenheit and Fahrenheit into Celsius. You know, you got 5/9 and 9/5 and stuff like that. That's a conversion factor. And there's nothing fancy about it. But there is something fancy about Newton's constant, this gravitational factor, G. About, let's see, 250 years after Newton developed this, Einstein developed the theory of relativity. And the theory of relativity, his theory of gravitation is that space-time, the four-dimensional space-time that we live in, you know, the three spatial dimensions, X, Y, and Z, and time, the fourth dimension, become curved in the presence of intense gravitational fields. And so Einstein, you know, developed the theory of relativity, and that's when we start thinking about uh, really exotic things like black holes and neutron stars and pulsars and stuff like that. Now, I know all kinds of stuff about black holes, and I can tell you that the capital G is actually um, the gravitational factor that controls the size of the event horizon around any mass object that you have, a kilogram or, you know, 10 to the 30th kilograms or 10 to the 40th kilograms, you know, the size of the event, and the event horizon is the point beyond which you cannot escape going into the center of the black hole and getting smooshed down to zero volume. Right? So the event horizon of a black hole, the point of no return, is controlled by G. You know what else it's controlled by? It's controlled by the speed of light, c. You know that famous equation E equals mc squared? C squared, that's the square of the speed of light. And that's also in the dimensions of a black hole, G and c squared. And then the mass of the black hole itself. It's kind of interesting. But, you know, we've used Sir Isaac Newton's theory. You know, NASA uses it all the time. It's pretty good for getting things, you know, to the moon, to Mars and stuff. GPS, however, if you need the precision of parking something within a few meters, you know, a circle of a few meters radius, you need the theory of relativity. So the GPS system uses Einstein's theory of relativity. But for the most of NASA stuff, where they just have to hit you know, a planet, you know, and get, you know, in the right, you know, few square miles, they have to use, they only need gravitational, Newton's theory of universal gravitation. All right, number two, we're going to work on a satellite example here together. Let's take a look at this. So we're going to put universal gravitation and centripetal force together. And the ones that we're going to think about are the Earth, the mass of which is capital M, and then a spacecraft, a satellite that's orbiting Earth, and its mass is M subscript S. Now, NASA sets the distance to whatever it wants. So far above the surface of the Earth, or technically so far from the center of the Earth, and it uses rockets to put it up there in the orbit. So they got to know what they're doing, and what they're doing is using centripetal acceleration concepts and universal gravitation to figure out how to operate spacecraft at any orbital distance that they want. So what we're going to try to do is a circular orbit. The elliptical orbit, a lot of satellites that are up there, like spy satellites, are on elliptical orbits, but we got a ton of stuff on regular circular orbits. So that's what we're going to work on. So here's the two formulas. All right. On the left, Gm M subscript S over R squared. That's the F of F equals ma. And it's a gravitational F. Gravitational force of F equals ma. All right. So that's the interaction force between the spacecraft and the Earth itself. On the right side is the centripetal force. This is the ma. A is v squared over r. And the m is the mass of the spacecraft. So it's out there orbiting Earth. It has a certain mass, has a certain speed, or NASA wants to give it a certain speed. And they got to get it to the right orbital distance, r. All right, so you've got, those two things. Now we're putting them together. And mv squared over r, the centripetal force on the right side there, you could use that for any circular motion. I mean, if you have a circular train track in the basement at home at Christmas time, going around and around a circle, that's a horizontal circle, and, it's going to have a centripetal force that the railroad tracks have to provide to the railroad train, your model railroad. But this is orbital, and so it hooks up to the gravitational force law. All right. Now, you'll notice something that's really cool and very, very convenient. The mass of the spacecraft cancels left and right side. All right. Now, that is very, very nice, because what it means is that here's your leftovers, Gm over r squared and v squared over r. Look at that. Any orbital radius r and any orbital speed v, it doesn't matter what you put up there. You could put up a burrito from McDonald's in space, or you could put up a dump truck or something big like the space shuttle, and v squared over r is going to be the same. All right, because the mass cancels. All right, now let's get the r over to the left. All right, we'll cross multiply r from the bottom of the right-hand side over to the left. And here's our fairly simple equation. Now, if there were no such thing as uniform circular motion, you'd have a much more complicated equation. But we're doing circular motion, and we have tons of satellites that follow this formula here. So what this means is, if you know the orbital speed that you want, you can figure out the orbital radius. If you know the elevation you want, you could figure out, okay, how big do I have to make my rockets to get the right V for that radius, right? So here's a couple so let me just park this up here. And here's an example. If you know the radius for the orbit, you can figure out the required V and then design your rockets appropriately, all right? That's what they pay NASA to do. They figure out, all right, I've got to have so many seconds of burn, so many seconds of thrust, et cetera, and I'll get up there to the required orbital radius. Question? Let's see. I went back. Okay, see there's R's in the denominator of both sides. And so I parked the, first I canceled. And now I've got an R in the denominator on the right. See that? If I cross multiply to the numerator of the left, then it cancels, and one of the ones in the denominator on the left cancel. So you're left with GM over R. Okay, got it? All right, so now this is like a spy satellite. You want it low enough that it can, pick Vladimir Putin's pocket, visually anyways. Now we got satellites that can do that. Keep an eye on the Ruskies. Yeah, you got to have the right orbital distance. You design a nice telescope and you peer down inside their left earlobe, and you get all the secrets that you can see. Now, what if you need a certain orbital speed? All right, what if I want something orbiting the Earth at a certain period every day? So what if I want something to go above Florida twice per day? Once at noon and once at midnight. All right, I can do that. And all you got to do is figure out the required altitude and orbital radius. All right, and you'll get your orbital V. So a satellite now here's a special example of that. Something that we do all the time. A satellite that is fast enough to orbit once per day. All right, and that's what we call a geosynchronous satellite. All right, a geosynchronous satellite is a communication satellite. If you have Dish Network or what's that other one? The other Q's DirecTV, yeah, DirecTV. You get your satellite dish aimed, and then you just bolt it down because it ain't moving. It seems it's orbiting the Earth, but the Earth, yeah, it tilts to the right thing. And once you got a good strong signal, then you just bolt it in place, and you don't have to do anything about it. And because the Earth is spinning, and it is orbiting at the same rate, geosynchronous. So we have satellites that do that. So this is an example, GM over R equals V squared, of how NASA uses simple centripetal acceleration concepts and the law of universal gravitation to figure out what spacecraft, where to put them and, how fast to make them. Now, a couple comments about this. This is known as an inverse R squared force. The other inverse R squared force in nature is the electrical force, which we'll study this semester, in a few weeks. Because it's an inverse R squared force, mathematically using calculus, you could prove that the gravitational force has infinite range. In addition, since it's always attractive, it's never repulsive, the gravitational force can never be screened. So your left earlobe is theoretically interacting with the Andromeda galaxy and the constellation Andromeda and every other galaxy in the universe. They're so far away, though, that you don't really notice it. The only thing you really notice in your left earlobe or anything else in your body is good old terra firma, the Earth. But theoretically, yeah. Now, I want to talk about, before we take off for the day, these two guys, Edmond Halley and Sir Isaac Newton. And check out the hair. Actually, that's wigs. Thank God that's not the style to keep. Over there in England, the judges and stuff still wear those, in the courts over there in England, I guess. But these two guys are very. They were friends. Edmond Halley helped Isaac Newton came up with the money to publish his his famous book on the principles of natural philosophy. Principia, they call it. And Edmond Halley has an interesting story concerning comets. Now, Newton applied the law of universal gravitation, and he proved a couple things. First of all, the planets orbit the sun on ellipses. The Earth's orbit around the sun is almost a perfect circle, but it's not perfect. We can measure it. It is elliptical. And this one here, this elliptical orbit that's shown is highly elliptical. The person that found this law was named Johannes Kepler, and he was an astronomer. He didn't have telescopes until later in his career, and he noticed that the orbit of Mars was not a perfect circle. And Mars has a little bit more eccentricity to its orbit, so it's definitely, you can tell the orbit of Mars apart from a circle. But our orbit and the moon's orbit, it's very hard to tell visually. If I made a diagram of both, you'd be hard pressed to tell them apart. A perfect circle and the moon's orbit, perfect circle and Earth's orbit. But like comets and stuff orbit on elliptical orbits, asteroids and stuff, a lot of things have highly elliptical orbits. But supposedly the sun is at one of the foci of the ellipse, and that's what this diagram shows. All right. Another law that Kepler developed was this, that if you track a planet or a comet or anything else on an elliptical orbit, in equal orbital period, equal slices of orbital period, like 1 day or 1 month, it'll form these little wedges. The sharp part of the wedge is at the sun, and then the circular part or the curved part of the wedge is out there on the orbit. Those wedges, blue and white or alternating, theoretically, they all have the same area. Now, it's extremely difficult to calculate those areas, but I don't know how Kepler did it. And Sir Isaac Newton figured out mathematically using calculus and trig out the wazoo. Yeah, if gravity is an inverse r squared force, then definitely we have equal period, equal times, and equal areas. So those little pi wedges, they're kind of skinny out here. When the comet is moving over here between 8t and 7t, it's kind of poking along. It's just making a few meters per second, but yet the radii back to the sun are pretty long. So you got a long slivery pi wedge. Now down here at apogee or aphelion, here at 0t, the planet or the comet is really booking. It's because it's closer. Gravitation is stronger. So believe it or not, it's a free fall orbit. It happens to be elliptical. And so since it's closer, it's in a stronger gravitational field, and it's got more acceleration, more speed. Question? The T's are equal times. Okay, so it's like if that were like a typical comet, that would be like 3-month periods. Correct, in terms of time. Yes, different shapes though. Okay, so each is 0t to 1t is like one unit of time. 1t to 2t is another unit of time. Same. So it's like taking a strobe photograph and then sketching in the pi slices and then calculating the area of each pi slice. And it turns out that even though the pi slices are all different shapes, the area, so nobody gets ripped off. You know how like you're at home and it's Thanksgiving and your mom is slicing up the pie and somebody gets a bigger piece than you and you start to get cranky, but that's not the case. Gravitationally, that never happens. So it's really what the be a lesson to you. Now, the third law, Kepler discovered three laws of planetary motion. Newton has three laws of universal motion, and Kepler discovered three laws of planetary motion. He was looking at the planets, Mars, Jupiter, Saturn, Venus, Mercury, and Earth. And he said that the orbital distance average, if you take to the third power, it always forms the same proportion with the square of the orbital period. All right, so the average orbital distance for the Earth is 93 million miles, right, from the Earth to the Sun. So if you take that to the third power, and then take the 1 year orbital period for the Earth, and make a proportion of it, and then do the same thing for like the orbit of Mars. The orbit of Mars will form the same ratio. If you take its orbital distance to the third power and divide by the square of the Martian year. So Mars takes a little bit longer. Venus takes a little bit less. Venus has a shorter year and a smaller distance. Question? Really? How about an equation then? There it is. Okay, so now, so this is what Sir Isaac Newton figured out. Kepler figured it out for the planets. This is actually true for any pair of orbiting objects. The square of the period is equal to, now a big square bracket of, there's G, see G in there? The gravitational constant, and 4 pi squared up in the numerator. And then down in the denominator is the sum of the two masses. All right? And then over to the right, a to the third, Kelsey, is the average orbital distance. So you take that to the third, and you take the year, capital P, the orbital period, square that, and it always equals the same proportion, the square brackets. And so this is really Kepler's third law. This is actually how we calculate the mass of a black hole. You cannot see a black hole. You cannot observe a black hole. It's a black hole. No light escapes. But we can see things in the universe. We can see stars, like giant stars. The very first one that we found was in the constellation Cygnus, a summer constellation. Cygnus X1 is an X-ray source, a star that's so hot it puts out a lot of X-rays. And it was orbiting something. We couldn't see what it was orbiting. All right? And it was either something really small and not very bright, or it was a black hole. So we did our Kepler's, third law calculations, and we figured out, okay, it's got to be a black hole. And Cygnus X1 is one of the most famous black holes. And now we've got dozens and dozens. We even see ginormous black holes in the center of the galaxy. And the Milky Way galaxy, we have a black hole that's like several million times the mass of the sun. And you know what? We think it's eating up other stars whole. Can you believe it? Like the sun just all of a sudden disappearing down the gullet of a black hole. Oh my goodness. That's how big that one is in the center of our, and we think that every galaxy's got one like that. Every galaxy that we've looked at, pretty much, we can see there's a big, ginormous black hole gobbling up other stars. It's kind of cool. And how we know what their mass is? We measure the period, P, we measure the orbital distance if we can. And then we can figure out M1 and M2. And it's pretty cool the way it works out. Now, we're not going to be doing astrophysics calculations, but we are going to be talking about these laws. Now, that's the stuff that Sir Isaac Newton developed, and he didn't tell anybody about it. Matter of fact, Halley at the same time, he was interested in comets, and he had been looking at comets, and he thought, look, I think these things are on elliptical orbits. And so he's talking with Sir Isaac Newton, one day, they're having a cup of coffee or something at Starbucks or out in the apple orchard trying to get conked on the head again by an apple. And he says, look, Sir Isaac, Edmond Halley wasn't a sir. He was just a regular guy. He said, look, Sir Isaac, I think these comets that I'm studying, they appear to be elliptical orbits. And so Sir Isaac Newton says, yeah, I got that. I figured that out like 20 years ago. And he figured out these three laws. Kepler found them by studying the planets. And then Sir Isaac Newton, a few decades after that, figured out it's got to be true because of inverse R squared force, universal gravitation. It takes a bazillion hours of calculus to do what he did, but he did it, and he says, "All right, Edmund, yeah, I got you. Yeah, it's elliptical, and yeah, it's gonna have equal areas and equal times, and then Kepler's third law. Remember that from Professor Kepler over there in Austria? Yeah, that still holds." And he said it will hold for anything, any pair of stars. Did you know that most stars in the universe come in pairs? They're binary stars. Most stars, at least in our galaxy, we look at all the stars. Our star is by itself. It's a single star. But most stars, like the Big Dipper, is got buku double star systems, binary star systems in it. So here's what Halley was saying. Kelsey, did you have a question? You're not going to have to plug in with that formula. That formula is just something for you to look at and admire and answer you're the one that asked for it, and I have it ready, but you're not going to have to calculate with that. But basically, it's just to say, this is one of our tools. And if we were taking a stroll through an observatory, I'd show you the telescope, and if it was during the day, you couldn't use it. But I could show you, this is our telescope. This is our Kepler's third law, Unknown caller. Doggone it. So anyways, Halley's studying these things, and he thinks, these comets are going to return periodically. And he was doing it for a bunch of comets. And in those days, telescopes were new, and they hadn't cataloged all the comets that we know about today. We know about thousands of comets. But he looked at a few of them from the historical record, and he said, you know what, Sir Isaac, my wonderful friend, Sir Isaac, I think that the comet of 1531, the days of King Henry VIII, and 1607, the days of Queen Elizabeth, 1682, the days of the Salem witch trials over in America. He said, that's the same comet, Sir Isaac Newton, and I predict that it's going to return in 1758. It's on an ellipse with a period of about 80-something years, 86 years or so. And we've seen it 3 times already in the last couple centuries, back in the days of King Henry VIII. And probably other people saw it, in the 86 years before King Henry VIII. They just didn't make a record of it in the history books, right? So Halley's saying to himself, this is my comet, and I predict 1758 it's going to return. Now, it turns out that both these cats were dead in 1758. But by God, it did return right at Christmas time. And that, my wonderful students, is a huge verification of the law of universal gravitation. The fact that you can use that theory to predict the future state, the time evolution of a comet that you cannot see except for a few months every 86 years. But if you know a little bit about it and track a little bit about it, we can predict it. And by God, it worked. And now we use it at the wazoo. The law of universal gravitation. And this is the triumphant prediction that told everybody around the world. This is like the shot heard around the world. 1758, and this is called Halley's Comet, or as some people pronounce it, Halley's Comet. And you guys will probably be alive for the next time it comes around, right? Hopefully. And this is, Galileo said, you can't just talk about stuff. It's got to be measurable. You've got to be able to measure stuff and then make a prediction and test to see if what you say is a bunch of gas vapor or is it on the money. And Halley and Newton were on the money. So forevermore, you have to say that the law of universal gravitation is locked in. It is verified. All right. Now, that's all I want to say for now about universal gravitation. Let us talk about exam number 1. The topics on exam 1, and we'll probably dismiss a few minutes early here. And if we do dismiss a few minutes early, you come up and double check your clicker things and stuff if you want. From day 1 up till today, so up until Halley's Comet. And what you want to do is concentrate on lecture, all right? And so what that means is if I talk about it in lecture, then it's fair game for the exam, all right? Also, homework. Now, we haven't had a huge amount of homework, but we're going to have a good, nice homework over the weekend for you guys to study with and work on. So you'll have that. Clicker questions also. So your number 1 priority for studying is lecture. And so hopefully you've taken some basic lecture notes. You can now go back and look at YouTube at each lecture. They're all recorded. And refine and polish your lecture notes. Also, what I will challenge you to do is, if you have a friend that you study with, or even if you're studying by yourself, as you go through your lecture notes, as you review the homework, as you review the clicker questions, always, and this is actually lecture notes primarily, as you go through the lecture notes, ask yourself this. Dr. B in this YouTube just spent the last 5 minutes talking about Edmond Halley and Sir Isaac Newton. How could he write a multiple choice or a true-false question about what he's been blabbing about for the last 5 minutes? And you can ask that same question. Matter of fact, how can Dr. B take that 5 minutes about Edmond Halley and Sir Isaac Newton and Halley's Comet, and how can he make 3 multiple choice questions? Because I could write an entire test about Halley's Comet the last 5 minutes, because it brings together a lot of stuff. So, but when you're going through your notes and stuff, always think, now, how is Dr. B going to set this up for a multiple choice question or a true false? Now, formulas, let's get to some of this other stuff here. What you're going to have to start with is a cover page. Now, there may be, and here's a cover page from exam 1 last semester. And see those velocity graphs? Yeah. And so I might put some diagrams on the cover page, and you can't really see it, but G is on there, negative 9.8 meters per second squared, and a few other little conversion factors. And every exam will have a cover page, and that's so that I can put information that I don't expect you to memorize. Right now, we don't have a lot of stuff that you can memorize, but the next exam, exam 2, and then especially exam 3, you'll be tempted to memorize, but there'll be a ton of stuff on the cover page. All right, so cover page, the first few questions will be formula matching, which we talked about last week. All right, so don't worry about memorizing formulas. Do worry about recognizing formulas. All right, slightly easier task. But yet you're going to get a point for each one you recognize. So as I've mentioned before, it'll be a formula on the left and then a concept or a definition or something over on the right, and you got to match, the left side to the right side. All right. I might have some true false, and I go back and forth on true false. Sometimes I don't have any. Sometimes I have a ton. Sometimes I just have a few. Some students do not like true false, and I can see a few of you shaking your head, so that's all right. But we may have a few. It won't be all true false. That would be cruel. And there'll be a ton of multiple choice. Now, remember, my test writing principle is this: to write a test that covers the basics and has plenty of basic questions, but yet also has some brain burners. So that if you've done the basic studying, you'll do okay. You might not get an A, but you won't flunk. But even if you do all kinds of studying and extra reading, there'll be a brain burner or two on there that will really cause you to think. And it will make it a challenge. You might be able to get an A, but it'll be a real challenge to ace it, to get 100%. All right, so tough to ace, tough to flunk. And usually my exams are pretty well turned out in that way. One or two iClicker items, so they'll usually calculations. Sometimes I put multiple choice in the clicker items. And if they are calculations, there'll be 2 or 3 points, maybe even 4 points, depending on how deluxe the calculation is. But not, as Kelsey was asking, are we going to have to do Kepler's third law? No, you're not going to be. But you may have velocity graphs. You may have 1/2 GT squared calculations. Okay. And if you do, and you're going to type it in using your clicker, and I'll analyze it in a spreadsheet, and it'll be separate from your Scantron score. So you'll have 2 scores that add up to 50. All right. And the other good thing about the iClicker question is they're self-paced. So when we're in lecture, you have to go, I set the pace for the clicker questions. I count down, okay, 10, 9, 8, and all that stuff. But on this one, you can do the clicker questions first, or you can do them last, or anywhere in between. It's up to you. And there'll be some instructions on how to do that. Okay, supplies. What do you need to bring? Okay, the raspberry colored Scantron with the UCF Pegasus logo. All right, 50 questions on the front, or 50 dots on the front, 50 on the back. Pencil and eraser. Okay, and calculator. But you may not use your cell phone. All right. And so that is the stuff that you need. All right. Now, if you forget your calculator, okay, and you're not going to use your cell phone, and it will just take you an extra minute or two to do some long division or some multiplication stuff. Like you're in sixth grade, you don't have a calculator. So you'll be all right if you don't. But if you bring your calculator, it will speed things up a little bit. Also, when you get here, I'm gonna confine you to the first several rows up toward the front, but one seat between every person. All right. So except for the front, I always keep the very front row open for people that come in late. So and I'll have a little seating chart up on the front, but basically it's going to be from row 2 and I don't know back to row 7 or something like that. Every other seat, that side, and in the middle, and that'll accommodate everybody. So you have plenty of elbow room and stuff. The other rule is, as I've mentioned before, if you're tardy, you can take the test up until the first person who started on time finishes. All right, so the first person, and that's usually about 20 minutes. So if you come after that first person finishes, you are SOL. But if you come before they do, then I'll cut you a break. Let's just start the test. You're going to have to hustle though. So the main thing is be ready and get your stuff here and try not to be too nervous. And then last thing, homework 4 of the weekend. I'll put some review questions in there too. All right, so you can use it kind of a study tool. All right, that's it. You're dismissed. I'll see you next week.